So let's take a look at motivating the integrating factor when you're solving differential equations first order, linear. Okay, so somebody observed that if you do the following, then things work out very nicely. If you do the derivative with respect to x of this quantity here, say mu, and then times y, then you get the following. Look, you will get d mu dx times y, okay, and then you're going to add to it mu and then dy dx. Let's just rewrite this a little bit as follows. So put the following mu and then dy dx plus and then d mu and then dx and then y. Now look what happens. If you take that differential equation, that basic one that says y prime plus py is equal to f, and if you multiply by mu, right, then you have mu and then y prime plus mu and then py, this is equal to f. So now look very carefully, look what happens. This mu times y prime, that's mu dy dx, it's already present, okay? So that means that this, whatever this is, mu p has to be equal to this, right here, because those are matching coefficients, right? They're both on y. You see that? This is y and this is y, this is therefore, so that means we can write down the following equation essentially, that d mu dx is equal to mu p. But now this is a separable equation. So in other words, you can separate, right? You're going to have the following. Being a bit careless with the notation here, but gets the idea across. You can separate things into d mu, like this. Let's do it this way. 1 over mu, and then d mu, and then here you're going to have p dx, you see? But then anti-differentiate both sides, so 1 over mu, and then d mu is equal to this antiderivative of p dx. Continue over here. So now when you anti-differentiate 1 over mu, you're going to have ln of the absolute value of u. And then after that, you will have whatever this is. We don't know what it is because we're not specified a particular p. Remember, this p here is really like, some function of x that's given to us, correct? Just like the f that appears over here is really like f of x, some function that's given to us. And then if you exponentiate both sides, you have e to the ln of the absolute value of mu. I meant to say mu there, okay? Mu, u looks about the same anyway. And then here's going to be e raised to the antiderivative of p dx. And e and ln are inverse functions. That means you can cancel off the effect of e and ln. You're going to have, therefore, mu is equal to e raised to this antiderivative of p dx. And then drop the bars and just do a plus or minus. So you're going to have mu is equal to plus or minus e raised to the antiderivative of p dx. And now you have a plus or minus here, and some people sometimes also ask about what happens with the c from doing the antiderivative. It doesn't really matter. Look, when you multiply this equation, when you begin with y prime plus py equals f. If you multiply, for example, by a negative, the negative would cancel off anyway, right? If you did something like this here, like plus or minus e raised to this antiderivative of p dx, okay, and then you attach like a c over here or something like that, okay? Then you would have plus or minus, let's see, e raised to the antiderivative of p dx, and then you can break this up into e to the c. But then e to the c is just a constant. In other words, you would have plus or minus e to the c, and then antiderivative of e p dx this way, okay? So you see this is a constant here. So if you multiply it across, the constant kind of cancels off anyway. So the point is that this integrating factor in its simplest form is this one right here. E raised to this antiderivative of p dx. That's it, whatever p happens to be. Anyway, I hope this is insightful and helpful. Leave a like!